Hello and welcome. Today we're going to do another example of finding multivariate extrema. So again, what the idea here is we have some f of x, comma y equal to z. We're going to do a specific example here of x to the fourth plus y to the fourth minus 4xy plus 2. Okay, so of course we're going to find critical points. We're going to find them. We have to find points with a flat tangent plane, and that's the point. That's a point where the gradient vector is equal to 0, 0, the zero vector. All right, so let's do this for this specific example. First, we have to take that gradient vector, and we're going to get 4x cubed minus 4y, and then we take the y derivative, and we're going to get 4y cubed minus 4x, and that's going to be equal to 0, 0. I can separate these out into single equations, and we're going to get clearly x cubed minus y, and we're going to get, for this one, y cubed equals x. It might be best to just graph these, because we know that is just a cubic. I'll do these in red. I'll do that one in red. It's going to look like that. Likewise, this is also a cubic, but it's going to be flipped over. It's going to have a flat slope like that, a vertical slope, but otherwise be basically symmetric. In fact, it will be symmetric about the 1, 1 line here. Okay, so what that means, of course, is we have solutions. We need to look for intersection points. So we need to find x, y combinations that satisfy both equations. So this one and that one. And that's really important that they satisfy both. You can't just pick numbers willy-nilly that solve one but don't solve the other. You have to check that both combinations solve it. And clearly what we have here, we have 3. We have 0, 0. Of course, that solves it both. We have 1, 1. We also have negative 1, negative 1. So those are the 3. The next we have to ask is, are these points minima? Are they maxima? Or are they neither? To answer this, of course, we need to use the second derivative test. All right, to do that, let's go to a new page. We have the gradient was equal to 4x cubed minus 4y plus, and then we have another component 4y cubed minus 4x, right? And that is fx there, and that is fy. Now we need to compute fxx, which is going to be 12x squared, fyy, which is going to be 12 y squared, and fxy, which we can compute from either one of these, which is going to be negative 4. All right, so we know that the second derivative test, you use that discriminant value, and that's equal to fxx times fyy minus fxy quantity squared. Okay, so in general, that's going to be 144 times x squared times y squared minus 16. Okay, so now we're going to look at that 0, 0 point. So d in this case is going to be negative 16, so that is less than 0. And if we look at the second derivative test, which we've shown in another video, we know that means that the point is neither a min or a max. Okay, so that's 1 point. Now let's look at 1, 1. d in this case is going to be 144 minus 16. That, of course, is a positive value. And if I look at fxx at 1, 1, it's going to be 12, which is positive. So that means it's a concave up surface. So what we have here is a local minimum. Okay, so we've collected up two answers. The final one is -1, -1. And that's going to give us a d is equal to, again, because we have here a quadratic polynomial, basically a quadratic function for both x and y. In the discriminant, what we're going to get again is the same discriminant value as before. It's positive. Likewise, fxx at -1, -1 is going to equal 12, which is also greater than 0. So everything's identical in these two cases. So what we have here basically is, again, a local minimum again. All right, so we found two local minimum and a neither. I think it's important for us to then go back and let's see if we can visualize. What we have here is f was equal to x to the fourth plus y to the fourth minus 4xy plus 2. Okay, we see those. They should be, of course, they should go big as x and y go away from 0 or the origin. So they should have that concave up bowl shape. But now when we look at that xy, we expect some dips at specific locations. And what we find is, of course, if I were to draw, let's put a big axis here. There's x, there's y, and z goes up. I'm not going to draw this completely accurately, but the idea is as follows. There's 1, 1 out there. There's -1, -1 out there. And we know that in this local region, that we're living in a little local minimum. So there's sort of a basin around it. And the same thing over there. That there's a little basin there. We also know that at the point 0, 0, at 0, 0, this is the point that's the saddle. We also know that as we go further away, if we go out far, far away from all of this, eventually those cubic or those quartic terms are going to dominate. We should see that this just gets really, really big all out there. But there is some point where there's a saddle connection between that. So it's sort of like a mountain pass between these two valleys. But if I go out this way, it should go up. All right, so that's the idea behind these things, is we have basically a saddle right there, and then we have a local min, and we also have a minimum here. Okay, so that gives us some idea of what the shape looks like of this surface just by looking at the function and looking at our results from our extrema analysis. So I hope that gives you a good approach to a solution here and how to use the second derivative test, compute gradient vectors, and so on. Thank you very much.